You may have thought, hey, the Laplace transform, it's just an integral. And differential equations, they're just equations that involve derivatives. So Laplace transforms, they might be useful in solving differential equations. If you're thinking that, you are so right. So today we're going to talk about what happens when we take the Laplace transform of a derivative. So let's take a look at some Laplace transforms of derivatives. So the Laplace transform of the first derivative, f prime of t of some function, is going to be the integral from 0 to infinity e to the negative st f prime of t dt. As you may have noticed, whenever we're taking the Laplace transform of something, that integral almost always demands that we use integration by parts. There's no difference here. We're going to have to do that. So integration by parts shows us that we have e to the negative st f of t evaluated from 0 to infinity plus s times the integral from 0 to infinity of e to the negative st f of t dt. Now, evaluating that first part, remember we're taking the limit as b approaches infinity of e to the negative b f of b here. So e to the negative s times b, that's going to be 1 over e to the sb, and b is going to be approaching infinity. That's going to be headed towards 0, even regardless of what f of b is headed towards as those b values approach infinity. So what we're going to end up with is something that zeroes out there for us, minus e to the negative s times 0, so negative s times 0 is 0, e to the 0 is 1, so we've got f of 0. So we have minus f of 0 from that entire first part. That's the only thing that's left standing. And then we're taking plus s times the integral from 0 to infinity, e to the negative st f of t dt. And we go, wait a minute, that's the Laplace transform of f of t. It is. So what we really have is negative f of 0 plus s times the Laplace transform of f of t. Luckily we have some nice notation, so the Laplace transform of lowercase f of t is simply capital F of s. So what I really have is s times capital F of s minus f of 0. And that is the Laplace transform of the first derivative of lowercase f. Now let's take a look at the Laplace transform of the second derivative. I'm going to save us all a little bit of mental anguish by not writing out the integration by parts that comes along, but what I'm going to tell you is it's going to follow a similar pattern, and what we're going to end up with instead is going to be minus f prime of 0 plus s times the Laplace transform of the first derivative of f. Well, luckily I know the first derivative of f. I know what the Laplace transform of that first derivative of f is. And so I'm going to plug in s times capital F of s minus f of 0 for the Laplace transform of my first derivative of f. And when I do that, what I end up with is s squared times capital F of s minus s times lowercase f of 0 minus f prime of 0. You might be catching on to a little bit of a nesting pattern that's happening here, and it continues. So if I was going to take the Laplace transform of the third derivative of lowercase f, what I would end up with is s cubed times capital F of s minus s squared times f of 0, lowercase f of 0, minus s times the first derivative of 0 minus the second derivative at 0. So this pattern, it continues. And what we have is a beautiful theorem that tells us about the transform of a derivative. So if f prime, and all of the derivatives of f up to the n minus first derivative of f are continuous on the interval 0 to infinity with 0 included, and are of exponential order, and if the nth derivative of t is piecewise continuous on that same interval from 0 to infinity with 0 included, then the Laplace transform of the nth derivative of lowercase f is going to equal s to the n times capital F of s minus s to the n minus 1 f of 0 minus s to the n minus 2 times the first derivative of f evaluated at 0, subtracting from there on until we get to the point where we're taking the n minus first derivative of f and evaluating it at 0 and subtracting that, where our capital F of s is just simply our Laplace transform of our lowercase f of t function. So this is awesome. Now we know what the transform of a derivative is for any derivative that we want. So now we get to talk about solving linear initial value problems with constant coefficients using the Laplace transform. So what we're going to have is we're going to find an unknown y of t that satisfies the differential equation and the initial conditions. That's like our goal. That's our set. We're going to have that y of t be in our differential equation. And then we're going to apply the Laplace transform. So we're going to take our transformed differential equation, and it's going to become an algebraic equation in some capital Y of s, right? That's what the Laplace transform does, is it takes lowercase y of t and it makes it an equation in capital Y of s. Then what we're going to do is we're going to solve for capital Y of s. And you guessed it, then we're going to apply the inverse Laplace transform to both sides of that equation, and that's going to give us the lowercase y of t that solves our original initial value problem. So that might seem a little bit strange that we're going to transform and then transform it back, but that's how we're going to solve differential equations using the Laplace transform. So let's take a look at an example where we're going to be solving the differential equation dy dt plus 3y equals 13 sine of 2t with an initial condition of y of 0 equals 6. We could use methods that we've used before to solve this differential equation. However, the Laplace transform makes it fairly simple to solve, and it can save us some trouble along the way or translate some of the calculus things that we had to do before into algebra things instead, thereby simplifying it. So we're going to work with the Laplace transform here. Also know that there are places where the Laplace transform is useful where we couldn't really use things that we've done before with them. So this will be one example of how we could work through this. So my first step is to find unknown y of t that satisfies a differential equation and initial conditions. I have it. Y is unknown. It satisfies it though. All right. Then I'm going to apply the Laplace transform. So I'm going to take the Laplace transform of dy dt plus 3 times the Laplace transform of y. That's going to equal 13 times the Laplace transform of sine of 2t. Now I can reference what I just did and know that the Laplace transform of my derivative here is going to equal s capital Y of s minus lowercase y of 0. And I know that the Laplace transform of y is just capital Y of s, so this is going to be 3 times capital Y of s. And it's going to equal 13 times the Laplace transform of sine of 2t is 2 over s squared plus 2 squared, or 4. So what I've done is it's become an algebraic equation in y of s. So I'm going to solve my transformed equation for capital Y of s. So the first thing you might notice is I have this minus lowercase y of 0 in there that's kind of holding things up. Luckily, I know what lowercase y of 0 is. It's 6. So this is really s capital Y of s minus 6 plus 3 times capital Y of s. And it equals 26 over s squared plus 4. Adding 6 to both sides, I get s times y of s plus 3 times y of s equals 26 over s squared plus 4 plus 6. Factoring out a capital Y of s, I get capital Y of s times the quantity s plus 3 equals 26 over s squared plus 4 plus 6. Dividing by s plus 3, I've got capital Y of s equals 26 over s squared plus 4 times s plus 3 plus 6 over s plus 3. And I can actually add these two fractions together if I multiply 6 times s squared plus 4. And what that leaves me with is 6s squared plus 50 over s squared plus 4 times the quantity s plus 3. So now I'm supposed to apply the inverse Laplace transform. So what I really want is the inverse Laplace transform of y of s, and that's going to equal the inverse Laplace transform of 6s squared plus 50 over s squared plus 4 times s plus 3. And in doing that, I'm going to get my solution of y of t. So really, I just have to find this inverse Laplace transform of this fraction I have here. So really, to do that, all I have to do is find the inverse Laplace transform of this fraction that I have here. Well, in order to find that, I'm going to need to use some partial fractions. So again, I'm going to go over to the side. We're going to do a little side work. So we have 6s squared plus 50 over s squared plus 4 times s plus 3. I want that to equal a over s plus 3 plus, now when I've got s squared plus something, then this is going to equal b times s plus c in my numerator of my second fraction over s squared plus 4. So that's a partial fraction thing that if you're not familiar with it, please go back and review that at some point. All right, and then we need to solve this thing. So common denominators for everybody gets us as squared plus 4a and gets us bs squared plus cs plus 3bs plus 3c all over s plus 3 times s squared plus 4. Now, my denominators are the same, so what I really have here is 6s squared plus 50 equals as squared plus 4a plus bs squared plus cs plus 3bs plus 3c. Alright, so now we're going to combine some like terms and set them equal to each other. So, if I look at my s squared terms, I've got 6s squared equals as squared plus bs squared. I have 50 equals 4a plus 3c. And hopefully you notice that there's some s terms that don't appear on the left-hand side but do on the right. So I have 0 on the left-hand side is going to equal, my s terms are going to be cs plus 3bs. So again, you can solve those, and solving those is going to give you a, b, and c. So again, I'm not going to work through the system of equations here, but when you do, you're going to get a equals 8, b equals -2, and c equals 6. So now we're going to do some substituting back to take our inverse transform of what we've broken down to be a nicer deal. So we're taking the inverse transform of 8 over s plus 3 plus -2s plus 6 over s squared plus 4. All right, breaking this up, we get y of t is going to equal 8 times the inverse transform of 1 over s plus 3 minus 2 times the inverse transform. I'm going to pull this fraction apart at the sum in the numerator. So this is going to be -2 s over s squared plus 4. And then what's left is 6 over s squared plus 4. And I'm going to notice that 4 is 2 squared. 6 has a 2 in it. So I'm going to pull out a 3. The inverse transform of 2 over s squared plus 2, or plus 4, sorry. So we get y of t equals, well, this is 8. The inverse transform of 1 over s plus 3 is e to the -3t. Then we have -2. This is cosine, because there's the s in the numerator, of 2, since the square root of 4 is 2t. Plus, we've got a 3. And since our constant's in the numerator, this is sine of that constant times t. So the Laplace transform has just given us the solution to that initial value problem of 8e to the -3t minus 2 cosine of 2t plus 3 sine of 2t.